Hi everyone. Let's solve the second question from weekly contest 326, that is distinct prime factors of product of array. So we are given an array of positive integers nums and we have to return the number of distinct prime factors in the product of the elements of nums, right? Note that a number greater than 1 is called prime if it is divisible by only 1 and itself, and an integer val1 is a factor of another integer val2 if val2 divides val1 is an integer, right? So what is given in the question is we are given an array of integers and we have to calculate the product of the whole array, and from that product we have to calculate this is actually 2 raised power 5, 3 raised power 2, 5 and 7. So we have to calculate the prime factors of this number of the product of that array, and we have to calculate the number of distinct prime factors it has. So as we can see, after calculating the product we get this quantity, and the prime factors we have are 2, 3, 5 and 7, right? So there are 4 distinct prime factors we get after we calculate the product of this array. But if we see, we cannot go ahead and calculate the whole product of the array and then calculate its prime factors. Why? Because the constraint given is that the length of the array can be to 10 raised power 4 and numbers can be anything between 2 to 1000, right? So we cannot store very large values and a very large array even. Let's say even we have 2 raised power 1000. We cannot store this inside of a variable, right? So we cannot calculate the product of the whole array and then calculate its prime factor. So what we can do is we can calculate prime factors for each and every element of this array. This is 2, this is 2 raised power 2, this is 3, 7, 2 into 5, 2 into 3, and then combine these later on. So we will get 2, 3, 5 and 7. So these are the distinct number of prime factors that we have in the product of the array, right? So let's see how we will do it. So what I have taken is a set. So this set S, it calculates all the combined prime factors of a number. So what is a set? Set cannot contain any duplicate values, right? And no two values in a set can be equal. So set will only insert a value if it is not already present inside of that set, right? So then we are traversing for each and every element and we are calculating the number of factors from this prime factors function. So here is the prime factors function. So what this function does is, we have a set right here. We again have a set, and inside of this for loop, we are traversing from I is equal to 2 to I into I less than equal to n. So a prime number, the smallest prime number is 2, right? So we have to go from 2 to n, right? But what is this condition? We have to go to I less than equal to, so according to this condition we are going I less than equal to root n. Now why is this? Because divisors always appear in pairs, right? For example, if we have 6, right? So if 2 divides 6, that means 6 by 2 also divides 6, right? So which is 3. So based on this logic, we go only till root n. There is no need to consider the numbers that are beyond root n, because as you can see here, if we have 2 here, right? So 2 is less than root n, right? 2 is less than root n, but 3 is greater than root n. But if we have calculated 2, we can easily calculate 3 also, right? Because if 2 divides this number, then 6 by 2 must also divide this number. So we can skip all the numbers from root n to n and we can simply calculate from 2 to root n. So we can easily calculate all the factors inside of this range. So that is what we have done for that condition, right? So let's move further. So after so I hope this condition is clear to you. then we are consuming all the numbers that all the 2, right, all the I that divide that number. Now we have to calculate the distinct numbers, right? So as we can see, we have we have 2 raised power 5 here and 3 raised power 2 here, right? So when I is equal to 2, right, when I is equal to 2 inside of this loop, then we have to consume all the 2 that divide this number, right? So we have to consume all the 2 5 times. So this is what this while loop is for. So we are consuming all the I that divide that number, and we are inserting inside of this set. So as set cannot contain any duplicate value, so set will only contain 2 once, right? So then there is also one condition, an edge case here. So the edge case is that if our number, right, the edge case is that we are checking that if n is greater than 1, then we have to insert that n also inside of this array. Oh, sorry, inside of this set, right? So why is so? So when we have something like 7 here, right, a prime number with power 1 only, if we have this, then we will fall out of this condition that we have, that is I into I less than equal to n, right? So why is so? So here, as we can see, after I is equal to 5, our number will be 7, right? So I into I is 25, and 25 is not less than 7, right? 25 is not less than 7. So our number will remain to be 7, right? So for this edge case, we have included that condition, and that edge case appears whenever we have a prime number with power 1 in the last, right? The biggest prime factor has power 1. So then this edge case appears, right? So after, so we will also insert this for this number also, right? We will insert this also inside of the set, and then we are simply returning this set from here. And after we have returned the set, we are storing in this another set called factors, and then all the elements in this factors set we are inserting inside of our set S, which is the set with combined prime factors for this for the product of the array, right? So and then after calculating prime factors for all the numbers, we are simply returning the size of the set, that are the number of distinct prime factors that we can have in a in the product of an array, right?